Okay, so today what we will do is I will be going to the next topic. I will be going to the next topic. So before that, you know, uh, wavelets are much more interesting, but due to lack of time or motive, we are not able to give enough attention. But as an example, let us see, two applications of wavelets which are very interesting. Okay. And after that, the topic which we would like to come to is this particular thing. Uh, Morphological image processing. Okay, now we are in a fix here. Module 4 contains wavelets, it contains color image processing, and it also contains morphological image processing. All the topics are interesting, and we cannot only cover half the topic and leave it just like that. So we'll be covering each of these topics a little bit maybe. And then afterwards maybe we'll go to module 5. In module 5 it's interesting, but then it's sort of complicated. There we intend to cover only half of the topics. Okay, so before I go to this morphological image processing, let me just take you to this very interesting MATLAB program. Okay, and let me try to convince you what actually a wavelet does. What actually a wavelet does. So keep an eye on this particular workspace on the left side. Keep an eye on the workspace on the left side. Okay. So here I have used one ready-made ECG wave, I guess, which was available in MATLAB. Okay. So what is the name of the wave? WECG is the wave. Let me plot and show you how does the wave look like. Okay, so here I can you see the screen? Darshan, can you see the screen? Okay, so here there is an ECG wave. Okay, as an ECG wave. So we are not doctors, but one thing is for sure. So most of them are not interested in these tiny changes that are going to occur. Rather, they will determine things maybe based on this particular thing, so-called QRS complex. I don't know what that thing is. You can go through MATLAB maybe, or maybe you can go through some medical journals. But as I understand, there are some low frequency things and then there are some high frequency things. These changes, what you can see here, these minute changes are of not of much interest to me. I will be rather interested in this spacing and maybe irregularities. Maybe this is what I'm interested in. Maybe these changes are what I'm interested in. I may not be interested in high frequencies. Now, if at all I have to select the lower frequencies and remove the high frequencies, there are two options. I could have gone for DFT. Now, DFT is a very specific thing where you have to mention, how many point DFT would you like to take, which frequency would you like to retain, which frequency would you like to remove, and can you go gradually to the lower frequencies? No, DFT doesn't provide me that freedom. Okay, so what I will do is I will use this particular wavelet called as Haar wavelet. I don't know whether I have covered the topic or not, but this is the topic that we are supposed to cover. So Haar wavelet is one of the type of wavelet given by this particular function here. Let me take you. The function is 1 by 2, 1 by 2, 1 by root 2, 1 by root 2, 1 by root 2, and minus 1 by root 2. What is that thing, by the way? Wait a second. Here. So derivation of a Haar wavelet is also very important question. It may come in exam also. But let me just show you. So unless you are curious, you wouldn't feel like reading it. Okay. So here, see, this is a typical Haar wavelet. So that means if at all I signal 1, 2, 3, 4 is my signal, I will take two samples at a time. Okay. I will take two samples. See here, this is the wavelet I am talking about. Suppose I have a sequence. Say it is 2, 4, 3, 2. Say this is the sequence that I have. First case, what I will do is I will take the numbers 2 and 4 and I will pass it through a impulse response 1 by root 2 into 2 plus 1 by root 2 into 4. Okay, 1 by root 2 into 2 plus 1 by root 2 into 4. Okay, that will be my first entry here. And then afterwards, I will take these two numbers, 1 by root 2 into 3 plus 1 by root 2 into 2. That will be my second number. See, I did not take entire sequence. I took the first half of the number, second half of the number, two numbers at a time. These will form the values that will come here. You might have realized from your DSP, you take an average that is low frequency. You take the difference, that will be high frequency. Now the second row here is 1 by root 2 and minus 1 by root 2. The second row is 1 by root 2 into 2 and then minus 1 by root 2 into 4. Okay, so that is the impulse response of this particular second column. So these are actually high frequencies. So we can see here the sequence 2, 3, 4, 3, 2. Once I apply a Haar wavelet, it has been broken down into low frequency component and high frequency component. So this is my multi-resolution. There is low resolution image and then there is the higher details. Okay, this is the low resolution. Now if at all I want to go further, maybe I can go one step further here. Now this will give me a DC average. If at all it is now, this will be giving me a DC average. Now suppose if at all I sequence which is of length 16, then I apply Haar decomposition. Then what's going to happen? First, I can one stage of decomposition, I will get 8 values in the low frequencies, 8 values in the higher frequencies. If at all I want to go further, so this will give me one lower resolution. Okay, this will give me one step lower resolution. If at all I want to go further, this 8 values, this will remain as it is. Higher frequencies will remain as it is. If this can I further, I can decompose it into 4 lower frequencies and 4 higher frequencies. Then I can go further. Then I will stop. At the end of the entire iteration, if at all I do this once, twice, thrice, 3 times, if at all I decompose, I will end up getting the average value here or the DC here. And then afterwards, various high resolution patterns will be here. Okay. So you got to do these things to have a feeling for it. Okay. So then there is a 4 cos 4 Harvard. So the derivation of this is very interesting, as I told you. Interesting or not, but it is important. So we have to go through it. So there is this particular formula. Based on this particular formula, you should be able to derive this particular matrix. Not that difficult. You remember the answer and maybe you can do it the other way. Okay. Now let us go back and see this particular example. As I told you, I have plotted one ECG wave and I may not be interested in the total length of the wave is, what is it? Let me show you here. It is 2048. Okay, the total length of the wave is 2048. So I am interested in only low frequency components. How lower? Let me just decompose this. As I told you, one stage of decomposition. Haar transform is the ready function that I am using. As I told you, I will take all 2 values, I will take at a time, then I will take all the low frequency values and I will pick only the lower frequencies here. A will get the lower frequencies, then there are details. Okay. So let me plot this thing. One stage of decomposition and what has just happened. Okay. What has just happened. Now we can see, now this particular wave here, whatever you can see, it is containing only the lower frequencies, one resolution less. Do you buy this particular argument, by the way? Wait a second, let me just convince you. Yes, now you can see there are 2 waves here. There are 2 waves here. See, the length of this particular sequence is 1024 and length of this sequence is 2048. So, and you can see here something values have been smoothened enough for analysis. Now we are doing a project where we have to transmit an ECG data. So if at all there is a bandwidth constraint and if at all you are trying to send it through an SMS, then they will charge on number of bits or something, right? I don't know. We might have to say the bandwidth. So we are not going to dumbly send the data as it is. Maybe we want to send only the lower frequencies for the analysis. Can I go further? Now, can I go for, see here the length has reduce. This is one stage of decomposition, enough for analysis, I guess. I can similarly go ahead. See, let me show you now how does a typical three-stage decomposition. What's going to happen with the three-stage decomposition? 2048 becomes 1024 after one stage. It's going to become 512 after second stage. Then maybe you can see here it has now become 256. And if at all I plot the thing, if at all I plot the thing, here it is much lower. I think still there are some hints to be picked from this. Still there are some hints to be picked from this. Depends what you actually want to do. Depends on what you actually want to do. So this is what multi-resolution and analysis empowers you with. This is what you also be curious. You also be curious. Take some data set and find out. Now you can see the kind of freedom that you get. Okay, so there are basically two types of programs that you will get here. One is the decomposition in uh, so it so happens that sometimes it can be on either sides, low frequency, high frequency, something like this, low, high, and then afterwards it may go on traveling in this location only, or sometimes you may have them on going on either sides. You have to use the right functions for the analysis. If at all you want to send the data, and you also understand that in most of the data, sometimes people are interested in only in lower frequencies just to have an outline of it, or maybe higher frequencies. Then you can manage, you can see. So this particular image here compared to 2048 is containing only 256 values, and maybe it is still holding up to those QRS complex. No, it has gone bad, right? So depends what you want to do with the data. By using the right filters, you can still hold on to those QRS complex. Okay, so there are a lot of demo files here in MATLAB. You can also go through them. So this was one application, okay, applied in one dimension or in two dimension also. The second very good application is steganography. So let us see if at all we have a steganography example here. Let me show you that. So what is steganography, by the way? What is steganography? Hmm? What is steganography? Now let me try to convince you what is meant by steganography by taking a whiteboard. Okay. So now I have given you an assignment in DSP, DIP class that you have to do this particular, take an image, do some filtering or something. Okay. So now what happens is Jishan takes the image and does the processing. Okay, so this is the image processed by Jishan, and he wants to submit the assignment. Then afterwards what happens? Hebbar goes to Jishan. Hebbar goes to Jishan. Hebbar has not done those assignments. Hebbar has not done those assignments. Jishan has taken pain to do the assignment. Hebbar takes the copy of Jishan's assignment only, renames it, and sends it. Both of them get marks. So since I have a biased opinion about Jishan, I will give Jishan less marks. And since Hebbar is a regular guy, I give him more marks. Is that fair, by the way? Is that fair? So that is why Jishan decides, no, I got to stop this particular thing. So what Jishan does is, Jishan is having this particular image of a tree or something which he has processed. Tree is a tree. Okay, there is tree. Okay, and what Jishan does is, Jishan decides to go for steganography, where he will hide his digital signatures, so that when I give him less marks and Hebbar gets more, Jishan can go and tell, I did the program, and you are simply giving more marks to that particular guy who has copied my program. So authentication, how does it do it, by the way? By putting a watermark, right? Have you seen those Sun TV watermark in those TVs, right? Now, if at all it does it that way, Hebbar will also come to know. He may rub that thing particular, right? So that's possible. So what Jishan does it, he will go for steganography, where he will hide his watermark in such a way that even Hebbar doesn't come to know. How does he do it, by the way? He decomposes his wave to get the low frequencies. So the tree is here. Okay, then he breaks it into higher, lower, high, lower on the left, or vertical, three higher frequencies. This is one stage of decomposition. Then he again does it further. He does it once again here, two stages of decomposition. So what that does, yeah, the tree is here, tree is here, then its outline is in this particular thing. Okay, then again all the remaining outlines are here. He goes to several stages of decomposition, then several stages of decomposition. Then what it does afterwards, he picks in one of these higher frequencies, in one of these higher frequencies, much higher frequencies, highest frequency. What it does is he puts a watermark. Here he puts an image, okay, with a big Z written. Okay, this property belongs to Jishan. That's his watermark. Okay, that's it. Not watermark. It's hidden. And then afterwards, what it does, he decomposes it once, decomposes it twice, decomposes it thrice using Wavelet. Then the last image, whatever he had, he is going to replace it. Then afterwards, it takes the inverse, it takes the inverse, takes the inverse. And the image looks as good as it is the original one. But what is the difference? Now this time there is a watermark embedded in the image, which Hebbar doesn't know. Hebbar copies out of ignorance. Then afterwards, Jishan tells, no, this belongs to me, and he has copied. Then how does he prove it, by the way? He takes the wave, does 3 stages of decomposition, and there it pops up. The Jishan's logo pops up. Isn't that cool? So the thing is called as steganography. If at all the thing is visible, Sun TV, it's visible. Star Plus, the icon, right? It's visible all the time. That's a watermark. But then it's a logo. We'll call it logo because it is there available all the time. Irritating. A watermark is one which is very pleasant. It's not going to affect the watching movie experience. We have seen so many times Star Plus logo on the scorecard only, right? There is score showing, then there is this logo, right? Because it's some retransmission or something. Star Plus on one side, ESPN on the other side, then Udaya TV trying to put that particular footage in their news, right? Their logo is there, it's all mismanaged, but they want to tell, the Star wants to tell that the video footage belongs to them. If at all it is the Sun TV, you can see it's watermark because it is very pleasant. It's not going to affect the whole movie watching experience or the cricket match watching experience. That's called as watermark. If at all you hide it so that nobody comes to know, but you want to claim the authority, then it's called as steganography. Usually it happens in a defense covered communications where a normal video file will be sent from one person to other. So whoever their interceptors from the enemy, they will think it's just a random video clip. But when you realize, when you find out that that particular thing, actually contains one more covered video inside of very small resolution. If at all you have an HD video, in that you can easily add a 240 pixel resolution video easily of same duration. Okay, you can also do that. So this is second type of communication. Now, do we have any files for this? Yes, here is an example. Here is an example. So here in this particular image, what they have done is, in this particular mandrel image, what they have done is, they have taken 3 stages of decomposition. 3 stages in the sense, make it smaller, make it smaller, make it smaller 3 times. And in the highest frequency, they have put this particular image. In highest frequency, they have pushed this particular image. Then they have gone on reconstructing. So this particular image actually contains the watermark of this particular animal. Okay, this is just an example of authorization. But do you see any perceivable differences by doing this particular image? No. But if at all somebody wants to claim, that's how it will be usually. Usually in YouTube and all, it so happens that you want to make a channel, use some ready audio belonging to some, some movie, and simply put the clip and you upload the video. Within 5 minutes, you will get a notice from YouTube of copyright violation. Okay, they know what thing is where, and the data might be copyrighted. So this particular idea, we did a project actually in 2012. That time, this streaming applications were less, and there was so many songs. Actually, nowadays you go for Wink Music and so they make money from ads. Earlier, that concept was not there. Steganography was very much relevant that time. Nowadays, do you see any online videos, by the way? Not videos actually, MP3 files, very difficult, right? You will get them legally on streaming applications. Earlier it was not like that. So a copyright was a issue. Very interesting topic, by the way, steganography. So we have seen 2 very, very interesting applications of watermarking. Wavelet especially, much more interesting, very easy to understand only. Okay, now let us stop the thing. So curious readers can go to textbooks. Not curious, those who want to score marks, they have to go to the important questions from the topic. Now let us stop that thing and let us go to the next topic, which is morphological image processing. Let us go to, wait a second. Now, Darshan, can you see the screen on your mobile? Can you see morphological image processing thing? What has happened? Hmm? You can't see? Okay. Hmm. Okay. So now let us talk about morphological image processing. A very interesting topic, and usually usual suspects questions will come here. Let us see what is this morphological image processing. Branch of biology, the form and structure of animals, extracting, mathematical morphology, tool for extracting image components that are useful in representation and description. That means, say, there's this particular large image that you have captured, and you want to know how many vehicles are parked. Now, how do you identify the vehicles, by the way? If at all you have taken the snap from the backside, maybe from the square number plates which they have in them, right? So, you might be realizing that government nowadays has made mandatory for a certain type of number plates have to be there, right? Standard dimensions, they come in standard dimension, standard forms. This is what government is trying to arrive to. So if at all you know what sort of thing you are searching for, maybe okay, tool for extracting image components that are useful in representation and description of region shape. So probably at the end of this particular chapter or two more chapters, we will be able to identify, if at all you know the shape of a particular thing that we are trying to find, we should be able to do that. Okay, maybe it's a symbolic thing. Okay, so morphological image processing is a uh, uh, several things that we can do together, but generalized. Okay, let us see what does it contain. So there is something like subset, there is something called as union, something called as intersection, there is complement, difference, reflection, trans, what is that, translation. We are not understanding anything. Let us go ahead further. Okay, let us go ahead further. Okay, now it's making sense. Okay, so there is an a and okay, so not of a. What is not of a? We are talking binary here. If a is not of a, means all ones become zero, all zero become one. Okay. Now here, see, this is the and operation. And is where both of them are having same values. Okay, see, this is image a and this is image b. Anding of image a and b resulted in a white here. White here because, see, this is and operation. The numbers, the colors did not add. This was also, this was what just happened here. See here, in this particular part this was black, in this particular part this was black. That is why this particular portion is black, remaining all portions have gone white. This is an or, this is an or, I would say this is intersection, right? This sort of intersection, this is sort of union, both of them combined. Okay, now you do not take this as a zero anded with a zero. Now you might be in an argument that zero anded with zero is a zero only. Yeah, one and zero anded with one should have been zero. You might feel no, this is about presence here and presence here, and means presence in this also, presence in this also, presence in both of them has to be compulsory. He should be there in second hour also, and he should be there in third also, something sort of that. Okay. Hmm. There is and, there is or, and then there is XOR. Okay, so it is there, whether it is there in both of them, then there is exception, otherwise not. Okay, okay. Let us see. Now let us come to one of the specific keywords, dilation. Trick is, we will understand dilation in common English and images shown, but for you to be able to represent them in terms of these sort of equations, that's the This is what you are supposed to do in exam. You should be able to write them in terms of equation. Okay. So what is, have you heard the term dilation, by the way? Have you heard the term dilation in English? So I unfortunately came to know about the term. I had a very bad experience of kidney stones. Okay, so whenever there are kidney stones, they give this particular a tablet, which will dilate all the nerves there, so that if at all the stone is stuck somewhere, the nerves will get wider. Okay, so dilate means make things wider, maybe make things wider. So a person whether is sick, what do they check for, by the way? First they see the pupils, right? So first symbol is, if at all the pupils are dilated, okay, you might have seen our pupils whenever we are awake in control, they will be very smaller, and the moment a person is unconscious, you see his eyes. That's what doctor checks, right? If somebody has fallen ill or is unconscious, critically ill, then he sees the eyes. He is checking for whether they have enlarged. That's called as dilation. Let us see what is meant by dilating an image. What is meant by dilating an image? Let us try and check. Okay, so see here, I have this particular image A, then this particular image. Okay. So this is a set. Okay, this is what I want to process with. This is my structuring element. This is my structuring element. The control of this element is in the center. Okay, knob is in the center. Now say I move this particular box here. Say I move this particular, yeah, switch off the mobiles. Hmm? Yeah. Now I take this particular box, this structuring element inside this. Can I move this box freely? Can I move this box freely? Yes, I can move. Now, till where can I go? The rule is, I take this particular box. Can I move this thing here? The condition is, this particular central dot of the box should not, this particular central dot of the structuring element should not exceed the boundary. Should not exceed the boundary. So I can, on this side, I can come in. I can move straight away till here. I can move straight away till here, right? So you can see the trajectory of the box. This is also moving. So till where I can go? I can come to this particular point, so that the box occupies this space here. Then I can move towards the north. Then we can go like this. So now I move this particular structure element inside this particular set. What do I get? The entire image now, whatever the box border of the box traced, that's my dilated image. So what just happened? What just happened? The entire image you can see here. This is what happened. The center of the box was here, and you could move till this particular line. And the outer part of the box, the places that it traced, that formed my processed image. So this particular thing is called as dilation. The entire box has, wherever the place, the center of the box has moved, the entire process called as dilation, represented by, the entire thing is represented by this particular process, represented by this particular process. Okay. Represented by this particular process. I hope you got this thing on. This will be much more convincing. Now see here, now instead of a smaller box, now we have a wider box whose dimensions actually match. Now if at all I take this particular box, and if at all I take this particular center of the box and I place it here, now we can see the box is on the left side, d by 4. Now, are you getting? Now this particular box occupies this particular space. Now you can see the outer boundary of box can move till this particular point. What about on the right side? Can it move? No, 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 no. So when you come to this particular point, the box cannot go further on the right side because the dot has stopped here. Similarly, so this here itself is the boundary. So similarly, down, when this particular box is moved, I can come till this particular point on the right side. This is what I can expand on the right side, half of the width of the structuring element. Then below I can go till the length. Okay. See here, then I move on the right side. So this is called as dilation. Entire box now has been dilated. Entire box has been dilated. Okay. Hmm? Getting an idea of what is meant by dilation. Okay. Now, on the contrary, okay, what sort of examples do we use actually? Where this particular dilation is used? Here, author says it is used in this particular applications where you have taken an image and it has been poorly scanned and you want to somehow join the points or make the edges rounder, maybe. So how are you going to do it? It's all about picking a proper structuring element. It's all about picking a proper structuring element, and there you can see once you process it, the image, the entire text is now looking good. You want thicker fonts, maybe. You want rounder edges, you go for this triangle. You want square edges, I will go for 1111 in all 9 places. That will give me square edges. Okay. So that was dilation. And on the other extreme, there is something called as erosion. What is eroding, by the way? What is meant by erosion? You take 1 kg of sand maybe and place it, a very dry sand, and place it on your rooftop where a very nice wind is blowing. And what's going to happen? As and when go, the entire thing slowly becomes smaller. The entire thing erodes. Okay. So that's what erosion. Okay. You make it thing slimmer maybe. So how are you going to do this particular thing? Something similar. Now you get this particular structuring element. Now the rule is, earlier I could move the dot till the boundary. Now the rule is I cannot move the outer layer of the box. The box should not exceed the original set. The structuring element cannot go outside the box at all. That means the dot will be somewhere around here, right? See here on this particular corner I come. Okay, that's where I stop. The dot remains here. So when I move from left to right, the dot moves this particular manner. Then I go to top. The box cannot come out. The structuring element cannot come out of the box. So I move all the sides. So now the place where earlier the place where the outer boundary of structuring element moved, that was my result. So that was dilation. Now it is the place where my center of the structuring element moved. So what actually happened? The entire image now became smaller. The entire image now becomes smaller. So this is called as erosion. Okay, this is called as erosion. So any other examples? Yes, now for example, now you can see. So this is very interesting. Now you can see, if at all I take this particular thing here, okay, see I fit this particular thing here. Oh, so what's the rule? The structuring element cannot escape the boundary of the set. Now can I go up? No, I'm limited. Can I go to the right side? No, till here only, right? I cannot go further. So this particular width is gone. This particular width is only thing I can move is I can move sideways. I can move sideways till this particular point, and then I stop. So the erosion by this particular structuring element has given me a straight line. So this erosion is represented by this particular sign. Dilation was represented by a plus sign, I think. This one. This was dilation. Okay. It is not an XOR. Okay. And this is erosion. Okay. This is erosion. Okay. They are dual, it seems. A very nice example. Okay. Here author wanted to pick out all those values which are greater than some, say 13 cross 13. So he is not interested. If at all you want to differentiate between the larger kidney stones that matter and some small particles. Okay. So which do not matter. So if at all this is the my ultrasound of my kidney stones taken, and if at all I want to find out all those which are greater than 3 mm, okay, size doesn't matter. Okay, of course, maybe a round and more. Then what I will do is, see here, he wanted to pick them greater than 13 cross 13. What author first does it, he erodes them. Okay, he erodes them. So what is the rule for erosion? If at all there is a box which is of 14 cross 14, the 13 cross 13 element can fit in it and it can move. It will create a dot. If at all there is a box of 15 cross 15, the 13 cross 13 element can fit in it. It can move a bit. If at all there is a box of 12 cross 12, Can a 13 cross 13 get into it? It cannot get into it. So all the smaller boxes where the 13 cross 13 structuring element could not get in were straight away removed, and only those boxes with size greater than 13 cross 13 they remain. Okay, now to regain the original position, afterwards dilation was conducted. So there you go, you picked only those which you wanted. So this is not something to be done automatically, but can be done. Okay, but can be done. So this is a nice example of see, we did not only use dilation, we did not use only erosion, a combination was used, a combination was used, something like that in bubbles, if at all, in OMR sets, and there are so many, there are so many places where you can use them. Okay, next class we will continue with opening and closing.